This will be posted.
Okay.
Sigma.
Okay, yeah, so there because at the so there's two, like, you know how there's two states in the capacitor, right?
Uh-huh.
Nothing
Yeah.
on it and everything on it,
Okay.
plus and minus. And so
Yeah.
here charges just flow across, and here charges don't flow across. So there would be no magnetic field here. Think about it. Because what is a magnetic field? It's caused by ch moving charges.
Right. Yeah, there's no magnetic field on the
So when
capacitor.
there's nothing to do with fully charged capacitors and magnetic fields. They're separate items.
No, I mean like the magnetic field on the inductor. Like, cause, bro, how do I draw? Hold on.
Oh yeah, okay, the spiral thingy, right? Like the slinky. Just gonna go like slinky.
Oops. Yeah, like let's say this is like in a circuit, right?
Hmm.
And then once the inductor has maximum magnetic field, then it pushes the current back onto the capacitor, right? To charge the capacitor.
Yeah, so what happens is the capacitor tries to force current through the inductor, but when you know how inductors in essentially, yeah, they induct, so they refuse to take the current and instead send the same current back at the capacitor. And so there's a constant, like, kind of like playing catch with the current. They're going back and forth. That's what
Okay.
happens. It's like
Okay.
the capacitor sends out charge and the inductor sends out the induced current and it sends out the charge back to the capacitor.
Wait, the inductor sends the charge. Wait.
It sends, yeah, because like it creates the induced current.
Wait, I thought that once the inductor has maximum like magnetic field, like wouldn't it keep pushing the current this way? Because like it resists the change in like the direction of the current, right?
Yeah, Ben,
Like
we
I
can all
thought that it would
see.
just like go this way and turn this plate into the positive one.
Not no, because you know how the inductor it reduces change in current, and so if let's just say you have no capacitor here, right, and you just slide in the capacitor, and then
Hmm.
now there's a current moving this way, the inductor will resist it by creating a current in the opposite direction. The inductor just wants there to be no current
Right.
change.
But that's initially, right? Like after a long time, like the
After
inductor
a
is back,
long
it goes this way.
after a long time, yeah, it acts like a wire, but then it doesn't, nothing really happens because in this state you have a capacitor and you essentially have a wire, so you just have a short circuit.
Wait.
So
But I
just
thought that, wait, like doesn't this go into simple harmonic motion though?
yeah, so that's what I was trying to explain. It
Oh,
basically so the capacitor sends some charge over, the inductor sends that same amount back. Capacitor sends some over, inductor sends the same amount back. It's like playing catch.
okay.
It's like I send the ball over to you, think the ball of the current,
Okay.
and then you send the ball back to me. So this is the inductor, and this is the capacitor.
Okay. So so there is a point, right, where like, because you start with this plate being positive and this plate being negative, like you kind of switch it up, right? Like like once all
Not
of it goes
ex
to this side.
yeah, kind of like sends all the thing one way, and it sends part of the current this way and part of them back the other way. But
Okay.
LC circuits are less tested on this exam than um the most important thing you guys need to know, and that would
Which
be induct just straight up
Straight up inducted
inductance,
it
straight up inducting it, yeah,
inductance.
inducting all over the place.
Okay.
everywhere.
This is going to be posted, by the way, Ben.
Or more.
So
That's funny.
this question, like this type of question with the bar,
Wait, are we looking at the same thing?
you'll have to switch the page to question
Oh,
page number
wait a
7.
minute. How to switch page?
You click on it and
The arrows.
you click on the arrows, yeah.
Arrows.
Or you can just watch the screen share.
I'm just watching the screen share.
Yeah,
I'll just
so
watch the screen
See, yeah,
share.
it's
this
easier.
so
Oh, jeez.
this problem with the bar, you have the resistor
Oh, I love this problem. Not really.
and the bar is probably the most important one to learn in this entire unit because this will show up on almost any test you take.
Okay.
That or the you're moving through magnetic fields. Last year it was looked something like this on the exam.
When you say the exam, do you mean the
The
AP?
AP, the
The
AP,
mock or the actual
the
AP?
actual AP exam. This was the actual AP FRQ. So let me actually want to do that one. Actually, I don't want to do that one. I'm going to do PTSD, but
I don't really care about the AP too much. I just kind of care about like what.
the test,
Like,
yeah.
yeah.
And so the test is either going to have something like that. Any test is going to have something like this or this, probably. These are the two fundamentals of this unit.
Sigma.
And so
But neither of those would involve inductors, right?
neither of these involve inductors, no. So the main things, there's two things you need to know about inductors. Initially, resist current, become a wire. Those are the two main things you need to know about inductors. You also know like the rate of current, I believe it's called, like the equations to do with the inductor. But the calculus of the R's of the LC circuit is probably one of the less used ones on the exam or the test.
Okay. Oh, also,
So,
I have a question about
mhm.
FRQ number 8
Which page is
in
that?
the notes. It's I don't know. It didn't even
Wait, notes 8 or like FRQ 8?
it
Notes 8, right?
yeah. Notes, wait, yeah,
Go back,
notes
go back, go back.
FRQ number 8.
Wait for it. If only the resolution was worse. I could almost see it.
What's up?
How's it going?
A new member has
Good.
joined the Socket Academy Live.
This is
Oh,
true.
PMO,
So
PMO,
how long
PMO.
has this been going on for?
Oh, like
Uh,
15 minutes.
not too long.
Not too long.
You
Wait,
don't
the only question I have is for like part D. Like I just don't understand. Wait, like when you add a second identical resistor, how do you know that it's in parallel with the first one?
A second identical resistor connecting the rails at the bottom of the incline. So
Yeah.
think about it. We're drawing our circuit like this.
Mm-hmm.
And so we're going to add another resistor here. So let's draw in a more manageable format. We have our bar right here, right?
Yeah.
It's an excellent drawing of a bar.
Is this true? So then we have our resistor.
R resistor. Get it? Because it's like an R. Because it's like resistance.
This
Yeah, I
is
do.
true.
Yeah, yeah.
And then we also have our other resistor.
Oh.
And then
Oh,
you can just take this as the battery.
I've been enlightened. Yes.
Sigma.
So if you want to, we can run through this whole one because I mean we're on it. So, right.
Uh,
B
I
I L equals mg sine theta.
Yep, and then it's like you just yeah,
Yeah.
yeah. Okay.
yeah.
So if you're trying to find I, you're gonna you're gonna find first EMF, right?
Mm-hmm.
Equals I times R. R, sorry, I is E over R. And EMF is equal to the change in area
Times B.
times B. dA dt and dA dt
Wait,
equals
sorry.
to,
I'm
yeah,
sorry. How do you pronounce dA over dt? Like, what if you just say all the letters together? Like, what if you just tried that for me, real quick? Like, you just pretended it was like a word,
I
you know?
said it in my head. No, you're done.
What? What are you talking about? It's just like just a bunch of letters.
How about you do it for the crowd? Because this is dA over dt is equal to L times RV.
This is true. I actually, yes, this is true.
And over R, so this is equal to BLV over R times, this is multiplied by B times L because BIL equals to that. And that's equal to mg sine theta. So then we just do the math. So there, this way, this way, this way. I go this way, you go that way. That gives you the answer.
Wow.
P equals E squared. I like I squared R,
I
right?
also like that one. Great minds think alike, as they say.
This is true. And because I is equal to mg sine theta squared.
That's so tough.
Times 1 over times just R. Sorry. And this is true. So
Wait, is there an L down there? Wait, hold on.
BL squared. Because I is equal to mg sine theta over BL.
Oh, gotcha, gotcha.
And so
I was just looking at
if you
the.
look at these three parts, this shows up an absolute ton.
Like what? Like a whole ton? Like to the 2,000 pounds ton? Or
Yeah,
like 1,000
it's
kilograms?
massive, bro.
Like an imperial ton or a metric ton? How
Yeah.
much ton are we talking? Oh, okay. I
Yeah,
see.
so each of these three parts is a really common free response question on just every test you'll take.
Every test you.
Okay.
I love this song.
And so D, because we're looking at now, V is equal to mg sine theta, and I'm writing this specific way just so you can see later, over B squared L squared times R. And because R prime is equal to,
Is R prime REQ?
yeah.
This is true.
So this is a good problem to really understand.
Okay.
Oh, Unit 9, Unit 10, 11, 12. Oh, perfect. The lineup is crazy.
What?
Unit 10, Unit 11, Unit 12.
Okay.
Perfect lineup.
Did people do bad on the last unit?
Um, I believe so. Yeah, I was talking with Nzeza, Mr. Nzeza about it.
What
What
was
was
the
it?
average?
I was just about to ask, yeah.
Um, I don't think he, I don't know.
Wait, what did you two get?
What did I get?
No, that was the other two people in the call.
I got a 93.
Dang.
Uh,
Sigma,
I think I got a 95.
Sigma,
You guys are crazy. I got an 86 and I was happy with that. Jeez.
I'd
Sigma.
be happy with that too.
Yeah.
Oh my god, the way he's racing. So tough.
I got a
So
97 on TS tests.
Okay, well, no one asked you, so. No, that's crazy. Good job.
What's a
I'm more
magnet?
curious about how you do that with the mouse.
Carefully.
Wait,
Bro's,
you're doing this on Wow, that's insane.
bro's been around Worm too much. Sokka, do you like my visual background?
Absolutely beauteous. I would like to point out to everyone viewing this call to concentrate only on
That's
only
true.
Ben's background.
Sigma,
We
bro.
will be doing the multiple choice currently.
Ooh.
Oh,
A wire loop of area A is placed in a time varying but spatially uniform magnetic field that is perpendicular to the plane of the loop. Hmm. Can someone in the class tell me what the equation for EMF is?
DB or BDADT.
Yes, very good. So,
Oh, I'm sorry. I should have done the hold on. Wait, did that work? I should have done the
so here's what we're gonna do. We're gonna go like cancel the areas and then BT squared, t to the 1/2, integrated dt equals dB.
so E.
So B is equal to, I believe it's 2/3 B to the 3/2. That's just some basic calculus.
No, there's a T there.
There's a, sorry, it's not
It's
B.
okay, Sokka. You're perfect and can never commit any wrongs.
This is true.
This is
I
true.
believe the answer is E.
That's what I got as well.
That's what I would have did.
That's what I would accomplished.
This is true. So for part 2, we shall be using the right-hand rule.
Mm.
If one is to draw the fact that the velocity and the magnetic field are in the exact same directions,
Would it also be E?
I believe so, because the particles are not, the charges are not moving. So I believe that would be the correct answer.
wait, so if it wasn't like parallel,
Okay, so
would they?
let's do an exercise and say they were into the page. Let's
No.
believe. So
A.
V cross B, so we're gonna have the thumb into the page, and then the force would be towards the bottom for the left hand. So negative charges would be here, positive charges would be here. This would result in answer A. If it was question for Ben, if it was out of the page, what would the answer be?
It would be B.
This is true.
Wait, why is the negative on the bottom and positive on the top?
Left hand rule.
Left hand. Okay.
I use left hand rule for the negative, right hand rule for the positive. Or you can just reverse it. So, magnet is first moved down towards the loop of wire, then withdrawn upwards. So, north to south. So it goes like this and this. So, Alan, what is the current is the amount of magnetic flux through the loop increasing or decreasing initially?
Wait, when it's moved
Now
down
it's
to the wire?
increasing initially.
It's increasing initially, and then when it's being pulled out, it is decreasing. And so, because of Lenz's law, it'll initially fight against the change, and so it'll try and create a magnetic field upwards. And that happens when current is counterclockwise. So it starts counterclockwise, and then once it leaves, it wants to have wants to have more flux through it. It doesn't want the change in flux, so it'll create a clockwise current. So in classic Zeta test fashion, the answer is once again the letter E.
Wait, is that like a common Nazeza?
No, just last test, because apparently,
Apparently. Sorry.
I think 2 units ago, 1 unit ago, it's like mostly E's. That's a funny test.
Is there any test? Is there any specific letter this test we should be aware of?
$20. Super chat.
15. I'm kidding.
Give donos. Guys, the field decreases with time. No, I can't. I won't speak on that. I
I
plead the
was joking.
fifth. The
I was
field
joking.
decreases with time t according to the equation B equals A minus BT. So, guys, what's the EMF equation?
Change in area times B. Or,
Yeah, so no, we might need to
or
change
yeah,
the
either.
variables around.
Yeah.
So take the derivative of that, we get negative B times A, which is just L squared.
Hmm.
And then you divide by R, because,
We got I.
yeah,
This is true. I would just like to remind everybody that there are 9 minutes and 51 seconds
this is
left in the
true.
meeting.
And because the field is decreasing outside, out of the page, it'll add out of the page, and so that gives you counterclockwise. I swear this isn't scripted, but the answer is once again E.
Wait. So it's decrease. Okay, yeah. Makes sense. Makes sense.
So we're shoving the bar into the loop.
Hmm.
So initially, so the current is acting clockwise. Take your time when reading these diagrams, guys. They are confusing. So that it creates a field like this. And so this is the north side, this is the south side. So because you have a north and a south,
Wait. I'm confused. Why are there two circles in the loop?
so the loop currently is carrying a current I, right?
Ding.
And so, like if I were to draw it this way,
Hmm.
the current creates a magnetic field that looks like this.
Ding.
And
Oh,
they travel
gotcha.
like
Yeah. Okay,
this, with a
got it.
north and a south side. And because the magnet is north here, opposites attract, the force is towards the magnet.
Wait, the force is towards.
Because south, north, opposite poles on a magnet attract.
So if it was Okay, so you could just use right hand rule to say that, right?
You
Like
can
because
just you can just say like by the fact that opposite poles on a magnet attract. That's what I would say, because right hand rule adds to a lot more issues because there's no moving charges right here or moving currents. It's just the
so
fields are interlocking.
is there not a current?
There's a current, but you have to you kind of can, but it's much easier if you do it that way because you have to account for each point on the loop.
Okay, so if the current was in the other direction, it would be the same answer.
If the current was facing the other direction, this would be the north side. This would be the south side. It would be like this,
And then it would be a way. Okay, that makes sense
and
then.
there would be a way.
So you do use right hand rule to determine like which side is the North Pole and which side is South.
Yes, yeah,
Okay.
for
Okay,
the
that's
loop. I thought you were talking about the magnet, which is, yeah, I'm tweaking.
okay. Thank you, thank you.
Wait, so the right side of the loop. Wait, wait, never mind. Okay.
You forgot some. Yeah.
The left side of the loop in this case is the South Pole.
Yeah,
So it'll like attract the north of the magnet.
this is true.
Oh, okay.
So, instant the switch has been going for a long time. So, initially, we're chilling, nothing's happening, right? And then we have this. Instantaneously at point X, we have nothing. I have nothing.
Why?
Inductor. Our inductor initially says no current can pass.
But doesn't it have to like get to the inductor first?
What?
Just say the current flows at the speed of light. Just say it happens, okay?
I
Like,
think we need to take a relativistic approach for this one.
unfortunately, this is true. So, Ben, when they say instantaneous, like, and you have a capacitor that's open,
Hmm.
like, you just say that it acts like a wire.
Like
Because it only acts like a
capacitor,
wire for the tiniest amount of time before it starts charging, right? Because by instantaneous, it means essentially the instant that something important happens.
Okay.
Instantaneous is not at like the very split second afterwards. It's kind of weird. It's just
Yeah.
like instantaneous means whenever they want you to look at the important thing in the problem.
Wait, so I don't understand why you wouldn't like actually find the current. Wait.
Because it's passing through here and the inductor does the induced current. And so this acts like an open circuit initially, this entire area, because the inductor does not allow any current to pass through this area.
So there's nothing that even goes through the resistor.
Not, yeah, like the net current would be zero, yeah.
Wait, what does that mean?
Because like
Oh, because it's
there's,
going forward and pushing
yeah,
back.
although there would be a voltage across it.
yes, because they're in parallel.
Wait, so
But the
how do
entire voltage drop would be across this thing. It just eats the voltage.
the voltage would just be in the inductor. The
Yeah,
voltage.
it would just eat the voltage, yeah.
Okay. So in the instant after the switch is closed, is there current in the other? There's a current in the other resistor,
Yeah,
just not that
it
one.
only flows through this one.
So it would just be or epsilon over R. If
Through
it,
this, through that one, yeah.
okay, got it.
Then for the second part, this acts like it doesn't exist. So now we can just redraw it as this.
Wait for number seven.
Yeah.
Okay.
So we can just draw it as a parallel resistor. So essentially we just have the normal energy and like it acts like a parallel circuit, but there is the energy stored in the inductor according to the equation. I don't know what the equation is. I
One
forgot.
half Li squared, right?
1/2 Li squared. And so
Yeah, I think
I is equal to E over, it's equal to E over REQ, which is just R over 2, so just 2 then.
So is the right answer not one of the choices?
I got C for 7.
Oh,
Because the resistance is this, the current should be that.
No, wait. Is it C?
I thought it's
My math
4
doesn't match with my answer.
B in the numerator.
Times,
Yeah.
then there's some factor. It's either a 4 or something in front that we just happen to be missing. So we'll just run with that, but that's how we did it.
Wait, what? I'm confused.
I, that's the equation, and this is the I. This is what we got 4 times this. I don't understand why that's not an answer.
Wait, Alan, you said you got C?
I mean, my work doesn't match up with my answer. I might have. I'm not sure how I can do the math right
So
now.
D can't be an answer, E can't be an answer,
A can't really be an answer.
A can't really be an answer.
Just so you guys know, we have like 1 minute left until it kicks us out.
Yeah, just rejoin the meeting, but B
Yeah.
can't really be an answer.
Wait,
Just
why can't B be an answer?
it, I mean, then you'd have to have no factor despite them being in parallel, so
Oh, true.
I guess they just misplaced a factor. Again.
Wait, so how would you do that problem if one of the resistors was 2R?
It would just be
It
two,
would
it would just be E over, it'd be 2R, 1 over 2R, plus 1 over R, so that's
just
2 over 2R. It's just 2 over 3R. So it's just I equals 3E over 2R.
3E over. Oh, okay.
Just normal resistor adding things. As the switch has been closed for a long time, it's open at T equals to 0.
Hmm. That's weird. I get over 8. That can't be right.
So